I hope I'm audible. If someone can confirm once in the chat. Okay, thank you. Okay. So the pattern for these live sessions are also similar to last week's, where for people who are joining in for the first time, the pattern is we'll be dividing our session into two parts. The first 1 hour, we'll focus on solving numerical problems or MCQ type of problems, which you encounter in your final exams or your assignments. And in the later hour, we will discuss the code walkthroughs for each week. And in this week, we'll discuss about the coding of CNNs, and this will help you solve your code assignments. Okay, so let's get started with the first question. So this is the question: consider the following neural network f of w with the parameters w and the input x. And the neural network is very simple. It is a two-layer network with weights w2 and w1, and w2 is the output layer weight, and w1 is the inner hidden layer weight, and this is the composition. So the question says, if we use a normal cross entropy loss and we initialize weights w1 and w2 to 0, will the network be able to learn? So can maybe you can take a minute or two to answer this question. Here G is the non-activation. The activation function is tan h, not tan G. Sorry, it's tan h. Okay. So if you know the answer, just let me know in the chat. Will the question is, will the network be able to learn if they initialize the weights W1 and W2 to 0? Just a hint, think about in terms of your gradients. That will actually help you, because a network learns when there is some gradient. So if there is some non-zero gradients, then the network will learn. That's how you usually think about learning. So if you think about in terms of gradients, then you will be able to answer this particular question. Okay, let me answer. Let me show you the solution. So the answer is no. The network won't learn because there won't be any non-zero gradients, and hence, if there are no gradients at all, there will not be any updates to the weights for the network to learn. So let's see the process or the thought process behind this solution. So we are given that there are two weights, W1 and W2. So let's break it down step by step. Let's consider Z1 to be nothing but the uh, linear combination of weights W1 with input X. A1 is nothing but the activation on top of the Z1. That is nothing but G of Z1. And since W1 is initialized to 0, we know that Z1 is also 0. And tan H of 0 is 0. So that is why A1, the output after the first hidden layer, A1 is 0, because W1 is 0. And then this A1 now acts as an input to the second layer, which where the output Z2 is nothing but weight W2 into A1. So this Z2 is also again 0, because A1 is 0, and also at the same time W2 is also 0. So now look at in terms of gradients. So the first gradient with respect to the loss, dou L by dou W2, is nothing but dou L by dou Z2 into dou Z2 by dou W2. Here we just saw that dou Z2 by dou W2 is nothing but A1. If you differentiate dou Z, dou Z2 divided by dou W, with respect to dou W2, it is nothing but A1. And we know that A1 is what? 0. So this entire gradient, right, dou L by dou W2, that will become 0. Similarly, the next one, the gradient of loss with respect to W1 is nothing but this entire term. And in this entire term, we see that the values of dou Z2 by dou A1 is also 0. So that is why this entire term becomes 0. So hence, both the gradients are 0, and there will be no updates happening if you initialize your weights W's to 0. Okay, I'll just quickly pause for a second. Any questions or anything that is not clear on how to solve this problem? you can ask me, because this type of problems are expected to come in your exam or assignments. So please feel free to ask me anything that is not clear in the solution. Yeah.
Can you just show the question once more?
Sure. So basically, the question says that you have a simple neural network and you initializing the weights of the neural network to zero. And now the main question is, will the network be able to learn with such type of initialization?
Okay.
Okay. Any other questions or anything? Okay, then let's move on to the second one. So second one is also very similar. Now the question, instead of initializing the weights W1 and W2 to zero, we're initializing both of them to some constant real number. So W1 and W2 are equal, and both of them are initialized to a constant real number. Now, will the network learn or not? Just again look back into the gradients like I showed you for solution one, and think about it. If both W1 and W2 are initialized with the same constant real number, will the network learn now or not? If you know the answers, just post it in the chat. I mean, you can take any guesses. Like you, think about taking W1 and W2 if it's not as a real number one and two, so one or two, anything, and just plug in the values and check. What do you think that will happen? Okay, let me just give you the uh, yes, as pointed out in the chat by Ivan. Yes, the network won't learn. The problem remains the same, because here, even though we have non-zero gradients, but everything, all the weights in the model, right, will learn the same update, will have the same gradients, will learn the same patterns. So there is no diversity. So because of that, the network won't really learn anything, because even though you have two different weights, right, W and W2, both of them, since they started from the same number, the number of the amount of gradient updates and everything will be in the same way, and they'll only learn a similar type of a pattern. Hence, because of that, the network won't be able to learn anything. So this is called as symmetrical properties of neural networks. So it's uh, always good to break the symmetrical properties between the weights. So yeah, so the answer is the network won't be able to learn. Let's move on to a simpler question. So this is a question, and it's an MCQ type of a question. It says that why are CNNs better than fully connected neural networks for image type of data? So out of these all options, what do you think is the correct option? Just post it in the chat. Uh, it's not just one. There, so the actual answer is it's both one and two. So let's go with the options, both one after the other. First one, I think it is clearly evident as to why it is parameter efficient, because in a neural network, fully connected neural network, you connect every input node to every hidden layer. So the number of parameters is much more. Whereas in a CNN, you have a small kernel of size like 3 cross 3 or 5 cross 3, 5 cross 5, and they keep on sliding over the entire window. So now the number of parameters that are learnable in a CNN are just the parameters which are in that kernel matrix or the weight matrix. Whereas for fully connected, it's every possible combination of the previous layer with the current layer. So that is why it is much lesser parameters in CNN. So that is why option 1 is correct. Option 2 is also correct because CNNs by design have inductive bias. So what is inductive bias? It means that there is some type of prior information or some type of what is it? Yeah, prior information you have created when you're using CNNs when you have a certain type of data. So what I mean by that is when you're having a small kernel, your entire idea is that the images will have certain objects which have the information locally preserved. Like for example, if there's a dog in an image, so the tail of the dog will be at the back of the body of the dog. The what do you say? The tongue, the eyes will be at the front of the body. So all these pixels, right? They are locally in some manner or the other coherent exist with each other. The tail can't be in the front, whereas the mouth can't be in the back. That is never possible. So this type of local information is captured only if only when even if you look at the small local region which is looked by the kernel. So that type of prior information or biases you're having in your mind, that the data will have such type of objects where only a small localized what is only if you look at some localized way you can also get to information of what is actually happening in that particular image. So that is why we say that CNNs have some inductive bias of local invariance or translational invariance and spatial rotational invariance. So that is why CNNs also have some inductive bias for images. Okay. Is there any questions in these two options? If you want me to repeat anything, please let me know.
Yeah, I was disconnected a bit. So
Sure.
I think third is the right answer, right?
Yes, both 1 and 2 are correct. Yeah.
Okay, thank you.
Okay. Sure. Any other questions? Okay, let's move on. Okay, this is again a numerical question. So it says that imagine suppose we have an input image of the size 3 comma 34 64 comma 64 channels height and width, and your filter or kernel is of the size 3 comma 5 comma 5, and the number of filters we use are 3. If the particular what do you say CNN operation has a stride of 2 and 0 padding is used, what is the size of the output filter? So there is a formula which professor has also discussed. So just if you remember the formula, then this is just a 1 minute question. You just have to input the values and solve it. Just quickly pause for a minute. Please try it out on your own and post your answers in the chat. Okay. Let me show you the solution. So the answer is the output shape will be 3 comma 30 comma 30. So first we'll talk about how this 30 comes and why it is 3. So the 30 comes because the initial input size is 64, the kernel size is 5 cross 5. Now, since you all know that after convolution, usually the size of the image decreases. How much should it decrease? It depends upon how big your filter size is and what is the stride value, and if you're using padding or not. So here the filter size is 5, the stride is 2, and 0 is the padding. And what is the decrease in the size is given by this formula. The formula is nothing but output size equals to the original image size, which is w width or height, minus the kernel size, which is 5, plus 2 times the padding. Since padding is 0, so this 2p is 0, whole divided by s, which is the stride, plus 1. Now this entire value, we use the floor of this function because we don't want any decimal values or any, because sizes are usually integers. We do want to avoid that by taking the floor of this entire value. So if you just plug in the values, w is 64, 64 minus 5, which is 59, plus 0, that doesn't matter, 59 by 2, which is roughly approximately 29 point something, and then plus 1 is 30 point something, and floor function gives us 30. So that's how you get 30 comma 30. Now since we have three such filters of 3 comma 3 comma 3, so each 3 comma 5, so 3 comma 5 comma 5, so each 3 comma 5 comma 5 will generate this 30 cross 30. So in total we have three such 30 comma 30 images basically. So that output size is basically 3 comma 30 comma 30. So any questions or anything in this particular question? Any doubts or anything? Yeah, is there a question, Mishkat?
I joined just now. So can you please tell me what we're discussing today?
Okay, so today basically, like as every live session, we'll have some questions. So in today we already begin with three questions. So this is the fourth question which I was discussing, and we're talking about CNNs basically in today's session.
Sir, I had a doubt how that 30 by 30 will happen here.
I'll just answer. Yeah, 1 second. Let me just finish the previous. I'll just come to your question. Yeah, Mishkat.
So got it. Thank you.
Got it right. Okay, thank you. Yeah, Pavani, please go ahead.
Yes, in the output size, we got only 3. The value is approximately 3 into 30 you said. So how that 30 and 30 will come? 30
No,
by
no.
30.
Output we got is 30, right? Not 3. So it is 64 minus 5 divided by 2.
Yeah, okay. 30 we got.
Yeah, output size is 30. The 3 comes because we have 3 kernels, 3 filters.
Okay.
Yeah. So that is why we're getting the 3 in the first dimension. And 30 is the height and width after convolution, which is coming from this formula.
So 3 is coming because we have 3 channels, right?
No. We have 3 number of filters. Channels is different. So input image will have the first dimension is the number of channels. Whatever will be the number of channels, that will also be the same number in the filter size. The 3 is coming because the number of filters are 3 over here. So for example, if I change the number of filters to be 5, the output will be 5 comma 30 comma 30. So this first dimension of the output will depend on how many filters are you using here. Is that difference clear?
Yes, it's clear. Thank you.
Actually, it's a very important point. Actually, thank you for pointing out, because this is where most people get confused. They imagine the output will have this channel dimension. It is not related to channel. It is related to the number of filters we are using. So please make sure that is clear. Is there another question, Mishka?
No, sir.
Yeah. Okay. Let's move on to the next question. Again, a very simple question, MCQ. What are the key benefits of the pooling layer in the CNN architecture? Pick the correct statements out of these 4.
I think the answer is 4.
Okay, let's just wait for everyone.
What about 3, sir?
Okay. Yeah. So let's go to the answer. The actual answer is all of them. I think someone answered tapas. I think I've answered. The answer is actually all of them are true. Let's go option by option to discuss it. So what is pooling layer first? So pooling layer doesn't have any parameters, doesn't have any weights. That is basically a pooling layer's job is it will have a small size, window size like 3 comma 3 or 5 comma 5. It will look at that particular 3 comma 3 patch on the input image and just pick either a maximum value in that patch or an average value, or depending on what type of pooling has to be done. So here there is nothing to learn. There are no parameters to learn. That is why we say that the pooling layer will have reduced number of parameters compared to a normal CNN layer. So first point is true, parameter reduction. Second point is translation invariance. That is the standard property of any convolution. We need to have translation invariance. That is what inherent assumption is when you're using CNN's convolution. The third is compute benefit. Like I said,
Please, can you please tell again about the option 2?
okay, so
Yes. I know
translation.
that translation invariance does only benefit the convolution layer.
So what does translation invariance mean is, for example, if a dog is placed initially on the left side of the image,
Okay.
and now the dog is moved to the rightmost side.
Okay.
Irrespective of where the dog is there, you always, if you look at a local patch of that dog position, pixel positions, you can still predict whether it's a dog or not. You're able to understand. So this is translation invariance. Same logic applies for pooling also, right? If your dog is at a certain left side, the max pool will give a certain maximum pixel in that all dog pixels. Now, if the dog is on the rightmost side and you apply the same maximum pooling, you still get the same pixel as the maximum when you look at that local patch in the rightmost side of the image for the dog.
Okay, sir. Thank you.
Okay, sure. And then it is also compute benefit, like I said, because there are no parameters, there's no computation as such. Whereas if you see in convolution, you'll have to first do element wise multiplication and then summation. So there are two operations, right? Whereas in pooling, there is nothing. You just have to identify either the max or the average. That's it. So it's a compute benefit compared to the normal convolution. So that is why all the three are correct answers. Okay. Any questions or any doubts in any of the options? That
So this property applies to convolution filter also, convolution operation.
no. This, because in convolution operator there is no parameter reduction. Like we need to convolution, there's no parameter reduction compared to pooling, right? Obviously, if you compare convolution operation in general with respect to fully connected, then it's parameter reduction. But if you compare it with pooling, there's no parameter reduction. So, and there's not really any benefit of compute when you compare to pooling in convolution. So this is actually with respect to the standard convolution and pooling, basically, the differences.
Okay, thank you.
Let's go to this question 6. So here again, it's an MCQ option. So the question says, in a standard convolution neural network, what type of features are typically captured by different layers? So as you know that CNN can have multiple layers, multiple convolution layers. Sometimes it goes from 50 layers, 150 layers also. So there are certain initial layers which we call the shallow layers, and there are certain layers at the end which we call the deeper layers. So the question is, what type of features are you typically captured by these shallow and deeper layers? So
I
just
think
pose.
it is D.
Sorry.
It is D. Both low and high level features are captured.
Okay, let's just wait for everyone else to also look at the options. If you know the answer, just post it in the chat. I'll discuss it in a minute. I think since people have already answered, the correct answer is B. So let's go ahead and discuss all the options one by one. So first option, okay, first before that, let's see what shallow and deeper layers, like I said. So shallow layers initially have the tendency, because they're looking at the first small elements pixel wise, right? Because the image you're capturing, after pre-processing the image on the first few layers, you're looking at every pixel to pixel, because the kernel is a small 3 by 3, right? So you look at every that small patch of 9 pixel in every first layer. So the images or the features that are learned right after this initial layers is all small features like edges, or corners, or like some type of other curves, those type of things. But as you go deeper and deeper, the now like for example, if layer 1 is looking at 9 pixels, layer 2 will look at 9 pixels of the previous layer. So inherently of the input layer, it is looking at approximately 81 pixels. So you see there's a exponential increase in field of view as you go deeper and deeper. So that is why, if for example, if the first layer is is able to identify features like edges and corners, the later layers or the deeper layers will combine these edges and corners and create more complex shapes or features. So that is why we say that always the first layers will capture low level features like edges, textures. Last layers will capture high level features like objects or other contents. So out of all the options, the only option that satisfies this logic is option B, where the shallow layers capture the low level features and the deeper layers capture the high level features. Okay. Any question or doubt in this particular option? Anything that is unclear, please let me know. Okay. So if this is clear, then let's move to the code walkthrough for today. So the questions were pretty simple. They were, if you understood how a CNN works, I think these questions are easy to answer. Most of them will have something like these MCQs, but always remember there will be formulaic questions like this. So you'll have to learn the formula and go. Apart from that, it's all based on the theory part of it, like how the neural networks, what do they do inherently. Let me
Um,
just.
already found these videos from the problem solving session under the
Uh-huh.
content. But I'm not found that coding part that you can explain in the session. That coding I'm not getting in the problem solving session.
You mean the
How can we
recording
get
or the
no not recording coding link? I mean
the notebook itself?
yes, that one.
Okay, so that is available on this GitHub link. I'll just open the GitHub link itself. Maybe I'll post it in the chat also. So there's our GitHub link called as DL for CV 2024. So in this, you have all the weekly notebooks. So I'll just share this link in the chat. If you have a common group also, right, with all the other students, please share this.
Yeah, sure. Thanks. Thank you, sir.
Yeah, no problem. So all the weekly, it's basically it keeps on updating week by week. If you see, so currently it's just fourth week because that's what we are doing current live session. So every week we update it over here. Okay. So let's go into the code walkthrough for today session. So in today's session, we'll discuss three important types of CNN networks, which is the LeNet, AlexNet, and VGG network. LeNet was, I think, the very first neural network which Jan LeCun worked during his, I think, postgrad or something. I'm not very sure, but it was very old. Then AlexNet came in 2011 or 12. I'm not sure exact year, but around that time. And AlexNet kind of used GPUs for training, and that's how this entire boom of deep learning with help of GPUs has happened. That paved the way for so many new algorithms and models in today's world. So that was one of the turning points of deep learning history. And then VGG is a relatively newer model compared to AlexNet. But obviously, apart from VGG, even further models have come like ResNet, DenseNet, InceptionNet. I don't think you'll have to worry about all those. But I think what is discussed in the lectures, right, what professors discussed, follow those architectures for now. But in today's world, obviously, there are much more refined convolution neural networks. So, yeah. So here we'll discuss how to first create the model, because like I said previously also, to create any neural network model, there are three major things you have to do. First is obviously how to create your data loaders using data sets. Then the second is you create your model network itself, the definition, like how many layers should it be, what type of dropout should be there, or batch normalization, different types of things. You define your network itself. Third part is the loop, the training loop, or the where you write a for loop which runs for multiple epochs and multiple updates, mini batches. It's a double for loop, and in that each for loop, inside that double for loop, you have your updates happening, the gradient updates. So these are the three main concepts. Obviously, fourth is where you evaluate. That is a standard step where you evaluate on your test accuracy, and that's what you report. Okay, so similarly, we do the same things here. So I believe and I hope that you all are familiar by now with what is a PyTorch, what is PyTorch, and like what are tensors, and what are the seeding, why is seed needed. All these concepts are clear because that's what we've discussed even last week also. So is there any doubt in that? Maybe I'll quickly brief you people if you are not familiar with what is the seeding process or what exactly is PyTorch and tensors. If anyone has any doubt in these concepts, please let me know. Yeah.
So can you please explain seeding again?
Sure, I'll explain seeing. But before that, anyone has a question as to what a tensor or a PyTorch, what is PyTorch exactly? I hope that is clear to everyone. Okay, so if that is clear, let's just talk about what seeding does. So, what exactly are we doing, trying to do in seed? Seed is basically it's like you fix a particular number when you have a random process. Now, why are we concerned with random processes? So, in your neural networks, right, all your weights we initialize them randomly. So, if for example, I have a simple three-layer MLP. Hello, yeah, Mishkat, tell me.
Yes, sir. Listening.
Yeah, okay, sure. So if I have a simple three-layer MLP and you also have a simple three-layer MLP, but we both initialize our weights differently. So it is very likely that the way we end up after 10 epochs are different. So for example, after 10 epochs, I can receive an accuracy of 90%, whereas after 10 epochs, you can get an accuracy of 89% or 91 for that reason. But this type of variations are not acceptable in industry or for very sensitive applications. So we need to, when I say that I got 90%, there should be some method or way for you also to receive that exact 90% number when you are deploying the model. For that reason, we fix these seeds. So when I say seed 42, it means that my weights are initialized the same way that your weights are initialized. It's not just weights, there are a lot of different random processes like how do you split your model into train test or the dropout, how randomly they should drop. A bunch of processes which depend on these randomness, right? All of them gets fixed the same way as they're fixed in my network, in your network, so that the reproducibility happens exact to the decimal point we get the accuracies same. So that is why it's very important to seed your models. Is that clear?
Yes, sir. It's clear. Thank you.
Okay, so as usual we first import all your necessary uh, modules or library packages. The first important one is torch, which basically helps you install use all the PyTorch components like tensors and the operations on tensors and all. Next is torch.nn. NN stands for neural networks. So it is it's a package in PyTorch library which basically helps you create your neural network models itself, like your convolution models or standard MLP models, or in the future you'll see models like RNN and all. So any type of neural network can be easily created with the help of this NN package called as neural network. Then torch.optim, as the name suggests, it is a package that is helpful in using the optimizers. So if you remember in the last week, professor has discussed bunch of different optimizers like simple gradient descent or RMS prop, Adam optimizer, Adagrad optimizer. So all of those optimizers are very well written and are easy to use using this package optim. Then comes the package called as functional. So it's again a part of neural network itself. So this functional contains certain operations like softmax. So softmax, you know, right? It is used as the output of neural networks, which where they convert the logits into probabilities between 0 and 1. It's not just softmax. You have all your activation functions present in this, like ReLU, tanhead, sigmoid. All of them will be present in this function. So this is all for these packages are all useful for creating the model. The next two packages, Torch Vision and Torch Vision.transforms, and the third also, .data loaders and subset. These three are useful for handling the data set. So like you know, data in our course at least, all our data sets consists of images. So and images you want to sometimes augment them before sending as an input. What type of augmentations you do, like slightly rotating the image or slightly make adding a noise in that image or changing the color of the image, minor modifications we do which we call as augmentations. So all of them are done using transforms. And data loaders and torch vision I'll explain as we go in the code. As usual, then we use two other standard Python libraries, Matplotlib for plotting, NumPy to handle the arrays and other type of evaluations. Okay. So once you import your statements, the first thing before doing anything is to set your seed. Like I just explained, very important to set your seed for reproducibility. Even in your assignments, please do not change your seeds. Whatever we give in your assignments are very dependent on the seed value. If you change the seed value, you won't get the same answer as we are expecting you to get, even though your code is correct. Okay. Next, we define some simple variables that are related to the data itself. Like for example, number of classes in our particular data set is 10. So we are using a CIFAR 10 data set, which is a very standard image classification data set. So image classification data set means you have an image and one object is present in that image, like a cat or a dog, and you have an associated label with that particular image. So together combined, you create a data set, the input image and the label. And CIFAR 10 is basically all the common types of objects which you see in your day-to-day life. So they collected, the CIFAR is an organization in Canada. They collected a bunch of such images for 10 different classes, simple classes like cat, dog is there, then mug is there, plane is there. I don't remember all the classes, but very simple everyday objects type of things. They have collected images from there, 10 different classes. So we are basically using that data set. So number of classes are 10, and how many samples we want per class, it's 2000. So here we are not using the entire data set because it's a huge data set. We are using a smaller subset of this data set where each class we are picking 2000 samples for that particular class. If you want to use, you can use the entire data set also. It just takes more time to run it. To make things simpler, we select a smaller subset. So for each class we have 2000 samples, and in total there are 10 classes, so we are just using 20,000 images to train our network. Okay. After that, next thing, important thing is to check whether your model has whether your system or your notebook has access to GPU or not. So that is where you use this command torch.device CUDA. If torch.CUDA is this command is there, right? Torch.CUDA is available. This is the command to see whether your particular notebook or local system can connect or access the GPU. If this is true, then you create a variable device where you say that where you store this particular CUDA device number like GPU 0 or GPU 1. If this is false, the device will become CPU. So always necessary to print and see whether you're running on CPU or GPU, because as you know, GPUs are way more faster because of parallel processing compared to CPU. And I mean, yeah, the training part, for example, if it takes 10 minutes, it can sometimes take 5 hours on CPU. If it takes 10 minutes on GPU, roughly. So make sure you're always connected to GPU. And to connect to GPU, I hope the process is clear on Collab. You just click on the connect to GPU. You have to go to the settings and change the runtime environment. Okay. So once you set your GPU, now let's talk about the data part. So before loading, sorry, can you repeat your question?
I was asking, like, what is this CUDA?
Oh, okay. So CUDA is basically a library that is written to access or to make the operations more efficient and run on GPU. So, for example, you are running any simple neural network training, right? So all that is written in PyTorch. Now PyTorch calls something called as CUDA kernels, which will talk with the GPU. It's like a intermediate language to talk to GPU, you can think.
Okay, okay.
Yeah. Okay. So let's go to the data set itself. So before loading the data set into our environment, we first need to talk about what are the different augmentations that we want to happen on this data set. That is a standard practice. So like I said, for that we use this transforms package. So you write transforms.compose. So this transform.compose basically collects all the different augmentations you want to be done on every image. So what are the different operations? These are three different operations. First is you resize your image to 32 cross 32. You can do it for anything. You can do it for not just 32. In our case, we pick 32 because the models which we are using are compatible with 32 input image size. But in recent years, it's not just 32. It can also be 224, 512 also. So that depends on what model you're using and what is it compatible with. So first,
So
Yes. Please go ahead.
Aren't we losing information by resizing?
Sure. We are losing, but originally itself CFAR is a 32 cross 32 image. So we're not really losing much.
Okay, got it.
Yeah. So there are some images, like I said, latest data sets also have higher resolution images, and then you reduce down to 224. 32 is very small in number, but since CFAR itself is in 32 already, I think it is in 32. That's why this doesn't really change much.
Okay, sir.
Okay. Then the next thing is we need to convert into two tensor. So just a question. I think we've discussed this in the previous live sessions. What type of format that the images have? Why do we have to convert to tensors? Any guesses? If we don't do this dot to tensor, will the data set work properly?
They are in arrays.
Sorry,
They usually be in arrays.
arrays is
data
fine.
type.
Array is the
Mm.
data structure. I'm talking about the data type.
Okay.
So it's usually something called as uint8, which is one type of format for images. It's not necessarily always that. So usually when you load images, right, from your local systems, that's where you have your data usually. So images are always loaded in a certain format, which is uint or other uint8 or uint, I think 32 or something, different formats. So those formats are not compatible with PyTorch. So we have to first convert those formatted input data types into tensors data types. So once you do that, that is basically done with this particular command, transforms to tensor. So always remember, very important, if you don't write this second line right, you will 90% of the times face an error unless the data which you already have has been converted to tensors somehow. Otherwise, if you're just picking an image and loading it directly, you won't be able to, it won't load directly as a tensor. Yeah, I think someone has it.
Like, what is that unit 8 you said?
It's a it's I think it is called as unsigned integer format. So integers, integers, floating, these are all different types of data types. So uint is the unsigned integer that's used usually because pixel values are I think between a certain range of 0 to 255. Because of that, that particular data type is optimal to store an image.
Okay, so it is a coding type, right?
It's a coding type, yeah. Again, uint is not the only format. There are a bunch of different. Standard is uint. You can just look up into different.
Any image would be like predefined in that unit 8 only.
No, that's what I'm saying. It's not necessarily always uint8. There are different formats. Uint8 is one of the common formats. Other common formats also exist for storing the images. But it's not in tensors. Mostly it's not in tensors. So that's why we convert to two tensors. And then once you convert into two tensors, next thing is we normalize. We normalize using a certain type of Gaussian distribution with certain means 0.5, 0.5, 0.5. And means and standard deviation again the same 0.5, 0.5. So I have two questions over here for you guys to answer. First question, why do we have to normalize? Second question, why do we have three values for normalizing, three means and three standard deviation? So just think about it, and yeah, I
Due
think someone.
to 3 dimensions of the image and normalized due to vast range of values, I guess.
So if you don't like, what is the benefit of normalize? Vast range is fine, but what is the benefit of normalizing?
Normalize, like if the range is too large, we bring it to 0 to 1. Like, if
But what is the benefit of doing that?
the neural network gets trained on similar kind of range.
True. In a way, you're correct. So first answer is obviously correct. 3 because we have 3 channels in an input image RGB. The second one is also you normalize to speed up your training process. Your model will work if you don't normalize, but it takes much longer time to converge, and sometimes it doesn't converge to a better local optima also. So normalization always brings all your features to a standard range, and standard range is usually 0 and 1, and then it speeds up your training process. Okay.
So why there is two, I mean 0.5, 0.5, 0.5 and again
Because-
0.5, 0.5.
Yeah, here one is for mean and one is for standard deviation.
Okay, sir. Thank you.
It's usually different values. In this case, we just kept it simple. Okay, so
For this transform you have done is the augmentation, right?
It's right.
But previously you said that we are just picking up some part of the CFAR 10 data set. Since we don't need so much amount of data, then why are we again transforming it if we have picked up sufficient amount of data from that?
Oh wait, we didn't pick up yet. This is just a variable I created. Now we'll next have to now load it. These are just the variables that I created over here. We want 2000 samples. We still didn't load the data set.
CFAR 10 contains how many images? So initially,
Think originally it contained around 50,000 to 100,000 something. I'm
okay,
not,
so we would be using that all images, right?
no, we're not using. We are just selecting 2,000 per class. So 20,000 we are selecting.
Okay, sir, but if we are like reducing its number already, then why we need to transform, right? That augmentation is done so as to increase the data size in case we don't have a large amount of data.
Right, but if you notice here, we haven't really augmented anything. We are just we are not creating more samples. We're just doing a simple type of resizing. It's number
Okay.
we're not increasing.
Uh-huh,
Your
right.
point will be valid when you're increasing the data set. Again, we're not doing any increasing over here, right?
Okay.
Okay. So here so this transforms usually is used for augmentation. So the part over here is to understand if you ever want to augment something, this is where you need to go to. This is the part where you have to look to augment your images. That is transforms.compose and mention what all augmentations you want to do it here. Okay. Then once you define what transforms you have to do in this transform variable, now first you have to create something called as a data set. That's a particular type of, you can call it as a data structure in PyTorch to handle these data sets. So torchvision.datasets.cfar10. CFAR10 is already existing in PyTorch library. So you can just use this command to load the data set. So here you see what are we loading, what are the arguments we are giving while loading. First is the path to where the particular data should download to. So that is the directory or the path file to which the data will download. Next, we are loading either the train set or the test set. So CFAR 10, the split is already done by the people who collected the data set itself. They have a separate split, separate what is it, set for training and separate set for testing. So you can just specify which whether you want train, then you store it in your train data set. If you keep train false, that will become your test data set. And then you send the transform equal to you send your transforms argument. So now here you're loading the data set, right? So while loading, you do all these three operations. You resize, you convert to tensor, and you normalize each of your image. So that all three operations will happen on the back end when you're calling this, when you're sending this particular argument to this particular function. And then download true, that is you have to use it. That's how it downloads the data set. So these two, now you're creating your train dataset and test dataset with the help of Torch Vision. So Torch Vision is used to load the datasets, you can assume. Okay. So once you get your datasets, just for visualization purposes, we okay. Sorry. Here we now load the entire dataset first. Train and test. We're loading the entire huge dataset. But like I said, we don't want the huge dataset. We just want a subset. So how do you get the subset? You subset it based on the class label. For like I said, there are 10 classes, right? So you keep a track. You keep a track of the class label. So the first 2,000 images that belong to class 0, you just pick those. Similarly, the next 2,000 images that belong to class 1, you pick those. So that is what this entire for loop is doing. This for loop is basically saying that you iterate over the number of classes, which is 10, and where np.where is that condition. You check when your target is equal to a particular index, you store that. And then you create a subset of this data set. The subset is basically creating only the 2,000 samples from per class. You create a balanced train data set. So once you create,
Actually, I didn't understood the class indices function under the class index.
okay, function. You mean
For loop.
this one, right? np.where.
Yeah.
Yeah. So basically, here you have all the targets. So targets is what is basically the labels of all the images. And now we are putting a condition that if class index, like this for loop goes from 0 to 9, 10 classes, right? So first it goes to 0. So we're finding out all the target indices where the target is equals to 0, the first class. You get this command np dot where targets is all the class labels. In all the class labels, we're looking at only those class labels which have the class index of 0, because that's the first iteration, and we store those particular indices in class indices.
So we are accessing its first column, no, by writing 0 in the.
Yes.
Okay.
And then once you identify all the class indices, means basically, let's just say class 1, right, has 8,000 images. Now, out of these 8,000 indices, that class indices will have 8,000 values. Out of these 8, you pick a particular subset using this np.random the choice, which how much is the subset size should be, which we mentioned, right, previously, 2,000. So this will now chosen indices will select the 2,000 samples out of this 8,000 samples for only one class 1. And that indices you store in this balance indices list. Now you repeat for all the other classes and you keep on storing it in balance indices. And now with the help of this balance indices, you create a subset data set in this line. Once you create the subset data set, then you convert into a data loader. I'll explain the data loader, but before that, any other doubts in the subset, how we created, or the data set, or anything till now what we discussed?
This line in the subset train data set, comma balance data set. So balance data set is suppose 2000 images randomly picked from one class, and train data set is like whole set or.
Oh, okay. So balance data set contains all the classes. So if you see, it's a list, and we're always extending. Dot extend is basically this for loop runs for 10 times, right? So this balance indices will have 10 different items. Each item will again be a list of 2000 values.
Okay.
So this train data set has the whole data set, like 50,000 images, out of which this balance indices is just 20,000 images. You're picking those 20,000 images from this 50,000 images.
Okay.
And that actually is done. Don't worry about how it is done, because subset is a standard package or function which is present. It will automatically take care of it.
Okay, so it would pick a subset of balanced indices from the train data set.
Exactly. Both images and corresponding targets will automatically be picked. Okay. So once you pick your data set, now once you create your data set, next is you have to create a data loader. So difference between a data set and a data loader, a data set is where you just load all your images, and then you create your train test splits. If it's not there, you just create it. Or if you want to create subsets, you do that. You do your augmentations, everything on data sets. Once you do all those things, now you have to create batches, right? That's what we learned in mini batch gradient descent. You create batches of your entire data set. How do you create the batches? That is where data loader comes in. So data loader creates batches of your entire image in like depending on the batch size. For example, I'm mentioning batch size of 100. Since I have 20,000 images, a batch size of 100 will create approximately 200 batches. So I'm creating 200 batches for train. Similarly to one, I think test how many ever samples there. Correspondingly, those many number of batches will be created for test. So this data loader is where the data actually creates, the data set is actually split into different batches. So bunch of different questions I'll ask over here. First thing is, do you think that when you're creating the batches, after, like I said, 200 batches are created, are all the 200 batches loaded to the GPU or not? That's the question one. So the question is, like I said, that the entire data set is split into multiple batches with the help of this data set, and the batch consists of size 100. So are all these 200 batches loaded at one time on the GPU or not?
No, the batch, respective batch will be loaded during its training.
Correct. Okay, before that, I think there's a question. Repeat the difference. Okay, so the difference over here, Pavani, is data set basically handles the loading of the data set, transforming the data set, creating a subset of this data set, or splitting the data set into train and test. All of these are handled by the data set functionality. Data loader's main functionality is take the data set as an input which you created, and then you divide it into bunch of different batches. And data loader makes sure that a corresponding batch which will be now used to update the model. Only that will be loaded onto the GPU when you're training, not the all the batches. Then because then we are not using memory efficiently. So data loader's main job is create the batches and load those particular batches which will be used by the model to update it in particular iteration. And once that update is done, it will then send back to the main memory and again load a next batch onto the GPU RAM. I hope the difference is clear.
Yes, sir.
How to decide the batch size?
Good question. So yes, so batch size depends a lot on number of images you have firstly. So a standard practice is 32, 64, 128, 256. People also use 512. That's a very standard practice of batch size. And depends, like I said, depends on your number of images and depends again also on your model size. So you can try out a different values out of the standard values, and based on that you can also depends on your GPU RAM. If you have a very limited RAM, then reduce the batch size. For example, when you work with big models, right? So GPU RAM is fixed, like for example 16 GB, 32 GB. Now that entire RAM should accommodate your batch along with your model. So if your model gets bigger and bigger, the batch, if you're having, if the batch size is big, then there'll be a conflict of memory and you can't load the model or you can't load the batch. So if your model is huge, reduce the batch size. Worst case, batch size 1 also works when your model is like some LLMs kind of a model. People nowadays in all LLMs, most of the GPUs, they use batch size 1 to, if you have a smaller GPU RAM. So it depends on a bunch of different factors, but standard numbers are 32, 64, 128, 5.
Batch of one means single training
Exactly.
sample, no? So won't it be a stochastic one?
Exactly, it is a stochastic one, and I understand your next question will again be the convergence problem and everything. But you have to realize that people can't do anything else because the model itself is that huge, and they have a limitation as to the GPU. So the variance and all obviously will be taken care of other components in the network, like somehow you have more dropout or some type of other regularizers you add to the network to take care of that variance.
Okay.
So moving on, I think, yeah. Oh, another question I had. So as you can see in this data loader arguments, there's a argument called a shuffle. I'm shuffling my train loaders, but I'm not shuffling my false loader. So the question is, why should I shuffle my train data? Any question? Sorry, any guesses?
Batches are shuffled, right?
No, the shuffle is basically when you're creating the batches, right? So each time when you create a shuffle, when you say shuffle true, the batches created are different in every epoch.
In the randomness in the data.
True, but why is it needed?
See, for every course, different same images are there. If a dataset contains a different classes, each class had the same images. If we not shuffle, the images are loaded into the training image by image related to the same class. So if we shuffle, it will be it will be mixed with the other classes also. Then it may train properly.
It will overfit.
Right. Yeah. Both Pavani is correct, and the overfitting part is exactly correct. So part over here is if you there's a bias right at the end of the day. Neural networks train with the help of what they see in a small batches updates. So you get bias towards one class if you don't show diversity, and the model thinks there's only this type of class that is present. Is a simple answer. Okay. Now, once you create your data loaders, your first part is done, handling the data sets. Like I said, there are four main components. First is data loaders, creation of data loaders with the help of data sets. Now you're done with that. Second is creating the model. Now let's talk about the different models. So like I said, we'll talk about three different models: LeanNet, AlexNet, and VGG network. LeanNet, very simple model. They have just two convolution layers. Okay, before going to the model itself, let's just talk about how you create a model in a neural network model in PyTorch. All neural network models are created as classes. Whatever models you create, right? You're in future when you are doing your assignments also, you'll create your own personal neural networks. All neural network models you need to create as a class, and this class should inherit the main parent class nn.module. Like I said, nn is this package in PyTorch called neural network. Dot module is basically saying that this particular class which you created, it is inheriting all the properties of the neural network class which is written in PyTorch. Very important that you mention this inheritance nn dot module. Okay, before inheritance, everyone is familiar with OOPS concept, object oriented programming concepts, right? Is there anyone that is not clear? Because I'll be talking about them today a little bit.
Very basic.
Basic, very basic is fine. Like, what is a class? What are the functions in a class? I think that is enough if you understand. What is objects? Okay, assuming everyone knows what it is, then let's move ahead. So we first create the class and we inherit from the parent class and end dot module. We now you have to define two major functions in this class. That's all you need to do for any neural network that you create. What are the two major functions? Init function and forward function. So init function, like the name suggests, you initialize your network variables. Like, what are the number of layers you want? Like, you want 2 convolution layers and 3 fully connected layers. So all these things you create the in terms of the global variables. That is self.con1 is a global one type of global variable. Self.con2 is the second global variable. Like that, you initialize all the different layers that you want to create in the init function. In the forward function, you basically create how the data should flow in the network. Like, input will be x, right? Now where should the input go first? It should go to the first convolution layer, and then f dot relu is the activation. Then this output will go to the max pool with the stride 2. Now the output of the second will go to the input of the third. So you know that data flow, right? If you can visualize it going from one layer to another layer, that entire flow you need to mention in your forward function. And finally your output is returned from the forward function. That's it. These are the only two functions that you have to worry about when you're defining or creating your neural network in PyTorch. There are other functions.
So
Yes.
why don't we define max pool layers in the init function?
You can. There's no hard and fast rule. You can always create that also. F instead of f dot max pool, you can also create nn dot max pool 2D, and you can create that as a global variable. That is also possible. Even relu, for that reason, you can create as a global variable.
Like in TensorFlow, how we go is like go sequence wise, right? After convolution, if there is a if there is a ReLU or something, we go sequence wise. Unlike that, here we are distributing it into two classes. So is there any way like the same, like we go with the flow in the same direction, like without separating out, like you had done in this case?
You mean like you're saying can separate it out? Like, you don't want to write f dot relu outside and then self dot con1 inside. You
No,
want
no. Actually, what I was saying is, if we suppose in TensorFlow, if we had done this, then it would be con1, and then it would be max pool, then con2, then max pool 2, like that. So it would be follows one single sequence, right?
Oh, you can do that. Okay, sequential.
In this.
I get it. I get it. So that you can also create. That's. I think we have that example. 1 second. Yes, I'll explain. This is the part.
Okay.
nn dot sequential. So this is another type of. It's like multiple options you are given. You can do it this way, nn dot sequential, or you can also do it the way which we wrote in the first.
Okay.
I'll explain that when I come to that. Okay. So like I said, these are the main two functions you need to worry about while creating the PyTorch, init and forward. And obviously now the next question comes, where is the backward function? Because we have to do backward pass also, right? So that is where this nn dot module actually helps you. You don't have to worry. Every function calculating gradients, backward passes, how it should be done, that all is written in nn dot module. All you have to worry is you create these two functions, and accordingly all the other functions will change. Whatever layers you created, the backward functions will change accordingly. Whatever other functionalities you expect to happen, those all things are taken care of with this nn dot module. All you need to worry is just these two functions. And also remember this, to call this super linet self dot underscore underscore init underscore underscore brackets. So this is basically an oops concept. So it is basically telling that you're inheriting from this nn dot module and you're calling that construct. Don't worry if you don't understand that, but make sure that you just mention this line. Just assume it to be something very important that you need to do when you're using a class, when you're using inheritance in class.
One more thing, like in the con1, we are
Mhm.
getting like the filter size is the third dimension is 5, but in the contour we must the third dimension tells about the number of filters. So is it the same? Like
Sorry, can you repeat again?
I'm saying that if in the first convolution layer,
Mhm,
the
mhm, mhm.
the phi denotes the third dimension denotes the width of the filter, right?
Right, height and width of the kernel, 5.
So and in the second, the 5 denotes the number of filters we obtained.
No. Uh,
Actually, it converts into like it maintains its two dimension overall, no?
right, right. No, but my point is this con1 and con2 is okay. I'll tell you the argument wise. The first argument is the input channels that you're getting.
Okay.
The second is the output channels. How many output channels should be there? The third is the kernel size.
Okay. I thought it to be the dimension of this dimension of the image.
No. Dimension of image has nothing to do over here. It's
Okay.
just the because whatever be the dimension of image, you
Not for
accordingly
it.
no dimension of the okay. If you want, you can if you want to mention a different height and width of the filter, you can put it in brackets like this. You can
Okay.
put it in brackets and mention 5, 3.
Right. So
You
what
can
is
do
what
this.
does this denotes? What does three numbers denote?
Yeah, I'll just go back. First one is the input. The input which you are giving, right? What are the channels in the input? So that will be 3 because it's RGB, right? First layer. Next is 6 is the number of output channels after convolution, which is number of filters basically. That will be 6. And then fifth 5 is your stride kernel matrix basically. What is the not stride? Sorry, my bad. Is the kernel matrix height and width? If it's just one number, it is square matrix. If you want to have a rectangular kernel, you can mention in brackets whatever rectangles. In this only, you can also mention that again. I highly recommend go and look into this function nn.conf2d. You can mention a bunch of different things like stride, padding, all those things you can mention in this arguments.
Okay. And also the FC1 16.
Right. So here what happens is okay, good observation. Actually, I didn't come to that point. So what happens is after conv2d, after the second convolution layer, if you look, here is you're applying the second convolution layer. Then you get your output, and then you're doing a max pull, which will reduce the size further. Now, the this after this pointer, after the max pull, the x is in a tensor shape, like a matrix, a three-dimensional tensor, right? But linear only takes a two-dimensional output input basically. So we have to first flatten out one particular dimension of this x. So that flattening it out is what we're doing over here. Here we are flattening it out by multiplying 16 into 5 comma 5, which is all the which is this x shape, which is 16 comma 5 comma 5. That is the shape of this x that we flatten it out using this x dot view, and this value we send as an input to fc1. Is the flatten concept clear?
Flatten must be done in one dimension, no?
No, you flatten it. Basically, linear layer takes two values, two dimensions input. One will be the batch size, anyways.
No, yeah, but it would be row cross one, right? The flatten layer. Column will be one, no?
Yeah,
The
no,
flatten.
column won't be one. Not necessarily, right? Column.
He asked
Because
about the dimension of that flatten
Yeah,
dimension. That is a vector, single
no,
dimension.
no. That is my point. My point is, you're talking about this x. After this x, what will be the shape of this x, right? After x dot view is
after flattening, the dimension would be row into one. That is what I must.
no, not necessarily, right?
But it would contribute like each pixel or each would contribute to a single neuron, no? So that is
No, it doesn't have to necessarily be row comma 1. It will be basically row comma whatever number of hidden layers you want. Why is it just one? Number of not hidden layers, number of
each
nodes in
question
hidden.
one neuron. That's why.
Exactly, one neuron, right? That's what I'm saying. But you don't want just one neuron. You want all the 16 into 5 comma 5 neurons, right?
Yeah, but all the neurons would be placed vertically downwards, right?
Exactly. That is why.
So that makes my column one.
Uh, okay, so I understand here your confusion. So yes, if you think about it, the 16 comma 16 comma 5 it'll be treated as column one after the other. but we don't call it that way because you have another dimension of batch size also over here. You can't just call the column to be 1 over here. These are the, yeah, you can't call the column 1 because in your, when you're imagining what visualization part you're doing, you're taking one image and doing all the calculations. That's what how you usually visualize in the architecture. You take one particular image, you don't really talk about the batch dimension over there. Then you can do that. But when you're considering the batch dimension and the first most dimension, then you can't really call column 1 here because the nodes are there one after the other, but those all will become placed in the column dimension.
So basically, at the end of the convolution layer, we would get number of filters, right? And then it would be concatenated with a single layer, right?
Not just number of filters, right? Number of filters along with the output size, right? So if it's, if you, I don't know if I have that example. Okay, so for example, after this convolution, before, after the max pooling, the x, right, what will be the size of x? Batch size will be there. I'm ignoring batch size comma 16 comma 5 comma 5.
Right, 5 is the image dimension.
Image output size.
Okay,
Exactly.
I get it.
Exactly, that's my point. So now we have to multiply that 16 into 5 into 5. So you have this
Okay.
3-dimension multiplications, and all of those will become 1 node in the linear layer.
I got confused because the dimensions or the blocks mentioned in the block diagrams in the code or any other place, so it shows a single block.
Oh, no, it's not single. Yeah, a single block, but it'll have a bunch of filters.
But it
and
represents the image size. Okay.
Exactly.
I had a question.
Yeah, please go ahead.
In this neural network, do we add our own code in between any convolutions or in between any max pooling layers?
What do you mean by own code?
Own code means after ReLU max pool, I want to add some encryption related code. So I want to encrypt those bits before extract the features of an image. So do I do like that in this neural network?
Yes, you can. You can modify it. You can, after, it's not necessarily that you have to have ReLU max pool. If you want, if you have some other components in your network, you can always take those outputs, temporary outputs, and do some other operations and return those also.
Oh, okay. Thank you.
Yeah. Okay. So in the before sending to the linear layer, so we have to flatten it out and then send it to the linear layers. And after that, it's just one linear layer after the other, 3 linear layers we have, and the output is 10. Similarly, here also we see first linear layer, ReLU, second linear layer, ReLU, and then finally the third. Here we return always the logits. Don't worry, here we are not doing softmax. Softmax will be done somewhere else. Here we always output the logits. Okay, so I'll just quickly pause for a second.
Okay. That 120 in the FC1 is the other layers.
Other layers. So other first, the previous layers output will become the input right now. So yeah, so that 120 is here and 84. Any questions or any confusions in this network till now? Okay, there's a question: how we get global local dimensions of the what do you mean by global local dimensions of the variable, Ivan? Maybe if you can unmute, you can ask. Can you please elaborate on this local global dimensions of which variable are we talking about? Okay, maybe you just type it out. I'll just move on and then I'll get back to your question. Let's go to the another architecture, AlexNet. So this is not the original AlexNet. It has been a slightly modified version of this AlexNet for CFAR10. Original AlexNet is slightly different, but patterns remains the same. Okay, there's a question. Can we change the pre-trained networks architecture? Exactly, like I was saying, right? AlexNet, we've changed it a bit, modified AlexNet for CFAR10. We can always change any pre-trained network. So I think that part, fine-tuning part, when we come right in this, I think the videos have already been released. This particular, yesterday it has been released. So where we talk about fine-tuning, and in that case, we can always take any pre-trained network and modify the architecture, like freezing certain layers, updating certain other layers, adding extra layers. You can always modify any standard existing network in the PyTorch.
Okay, so we can change the architecture, but the weights would be freezed of the LXNet here, right? That is being told, right?
Here we're not importing. In this particular case, we don't have any frozen weights.
So why there is need to write LXNet, right? Is there something related to it in this code or something?
Oh, the name of the class.
Yes.
No. It's just for you people to know that this is an AlexNet type of an architecture.
Okay.
Yeah.
The way they used, there is nothing freezing of weights or anything.
No, that'll come next week. Next week, as in this week, you will see in the live session for next week, we'll discuss how to do that.
Okay.
So again, Alex pattern is similar for AlexNet. So here you can see we specifically mention those arguments. 3 is the input for convolution. 3 is what is the input channels. 64 is the output channels. Kernel size we want. If it's a square, you just mention a number. If you want rectangle, mention in brackets. You want stride. What is the stride? What is the padding? The default stride is 1, padding is 0. Padding 0 and 1, just look into the arguments, what they mean by it. So these are the different convolution layers. So AlexNet has 5 convolution layers and then 3 linear layers. That's the standard AlexNet architecture which people followed. And then you have your linear layers. This value is again coming from the flattened value 256 into 2 comma 2. And then you have different other layer values, and finally you output your 10. This is all you create in your init function, which is again a child of this parent package nn.module. And in the forward function, like I said, you mention how the data should flow. What all do you mention? You first start off with input X. You send it to first convolution, then ReLU, then max pool, then ReLU. Basically, step by step, layer after layer after layer. Then after that, you create your flattening vector using this x.view function. And then after these are just some conditions you put. If in case you're not correctly flattening out right with the dimensions, you just put a condition. Once you finish that proper flattening out, you just send it to the linear layers, and then as usual after the linear layers you call the ReLU functions and return the output. So same what we did for linear is the same thing, only difference is we put another extra condition to check if it's properly flattening it out or not. It's just for sanity check, you can think.
Like why we need to write that thing for flattening?
So here what difference is, previously we calculated prior and we gave a certain value 16 into 5 into 5. Here we are using a dynamic approach where we are saying ki we know the batch size of initial values. Whatever is not the coming from the batch size dimension, just multiply. That's what this -1 represents.
Okay.
So their point is, if sometimes it doesn't happen, right? If this -1, what we'll calculate, it's not equal to this values 4096. Sorry, not 4096, which is not equal to this 256 into 256 values, right? That will be a problem. Then the model will throw an error that mismatch in dimensions. Expected input to be something else, we got something else.
Right.
That is what we want to avoid. That's it. Okay. Again, next we'll come to another standard model called VGG network. Pattern again remains the same. Like you have two main functions, init and forward. Init here the way we created previously up till AlexNet and LeanNet, we created all these separately global variables, conv1, conv2, conv3, and then linear layers. But as I think Sayesh asked, why can't we do all of them in that one sequential? Like for example, like this nn.sequential, you create your entire network together. nn.linear first is the first linear layer, then ReLU layer, dropout layer, linear layer, all these values you create as it is, and you call this self.classifier. That's it. So here features are basically existing features of VGGNet, which I'll explain how we are getting those features that we are using this in this make layers. It's a bit different for VGGNet because we already have the network created in a certain way. That's what we are actually using those convolution layers which we create. That is we call as a features. And then classifier we create in an nn.sequential fashion. The only I wouldn't call it disadvantage. The only difference between using nn.sequential like this to create your network or to create a network like this is, when you create your network like this as you created in AlexNet and LeanNet, you have the option to get intermediate outputs Like, because if you create your network like this, after every X, maybe sometimes you want to use this X. Like someone asked, can I create some intermediate code of my own in between using the intermediate output? You can do this over here. Whereas if you create it like this, here you can't get intermediate, because NN sequential, what it does is takes the input, sends it to this stack of layers, and you can't directly outputs after the final layer. You can't get any intermediate outputs. So if you're sure that you're not using intermediate outputs, you can use NN sequential, more compact. You don't have to write this flow of the entire network. But if you want to use the intermediate outputs, I would suggest using the above way of creating the network. Yeah, I think there's a question. Nashkat, yeah, please go.
Yes, sir. So why there is no count for max pooling layer here?
No,
in
there
the
is,
GPU?
there is. So the max pooling con we create as a separate function, that because VGG itself is created in a bit different way. So that's why we created it in this particular layers. We created a separate function which we will call in this init function.
Okay, sir. Got it.
Yeah. Okay. So this is the three different type of networks. So now the second part is also done, where we create your networks. In this case, we created three, but usually you just have to create one neural network. Now let's go to the third part, where I told you that we have to create your for loops, basically the training loops. So that is what we are creating in this function called as train model function. So you don't have to create always a function. It's a programming choice, depending on the individual. Sometimes people create a function to make it more compact. Sometimes people just write all of this what we wrote inside as a separate code itself. They don't create a function. In this case, we created because since we have three different networks, we want to train all of them, and all of them will use the same training loop. So it'll be more what do you say? It's easy to abstract it and create it as a function. Okay. What do we do in train model? First thing first, you need to send your model to device. This is because if you don't send, by default, all your models are created on CPU, even the data set. So to truly access the GPU power, you need to first send your models to the device. Similarly, you also have to send your data to the device, but that you do it in a later step. Model first, you send it to the device. That's what here we say model dot to device. Even in your assignments, right? Make sure that you always send your especially when you in this as coming assignments and future, right? Make sure if it's a training type of a question where you have to train big networks, always send your model to device. Otherwise, it'll take a lot of time for you to complete the assignments. Once you send that, you can just print your model to see the architecture. So if we print that models here, sorry. Yeah. So as you can see, we print the LeNet. It's a simple 2 convolution and then 3 layer. That's what it just prints. Like what are the different layers there in that particular architecture. Okay. So you print your model, and then you create a bunch of different empty lists. These all, like the name suggests, right? These are just to keep track of your accuracy and losses. What is the training accuracy? What is the training loss? What is the validation accuracy? What is the validation loss? So I hope you all are familiar with train validation test. That part, it's a standard machine learning practices, whatever we do. So we just create a bunch of empty variables, empty lists actually, to keep track of these values. Now here is where the main loop starts. First, you outermost loop will be on the epochs, number of epochs you want to do it. You can define it. You can do it for 5, 10, 50. Again, depends on what is the GPU that is available for you. It actually depends on that, because sometimes if you have a very small GPU, small in the sense the compute power is not that great of the GPU, doing it for more epochs is just going to take a lot of time. So, but sometimes if you are capable of doing it you can do it for 100 epochs also. That is one way to do that. Another way is the convergence. Sometimes I'll explain in the bottom plots when you see, right, how the accuracy values come. With the plots, you can judge that after 5 or after few epochs like 1 to 5, the values are not really changing. You kind of plateau, or you kind of flatten out your accuracies. You're not improving or decreasing. So it means that going beyond certain number of epochs really doesn't help your network to learn anything. So usually you just stop at that particular epoch, after which it is plateauing. But you can try different values. There's no standard number of epochs that you have to use. Okay, the outermost loop talks about that. Then after immediately defining that, you create more, you set your model to a training phase. So Okay, a quick question. What does this model.train do? Why do we have to set this? What functions in the background that change when you do this model.train? Will the function work normally if you don't do model.train, or what is the problem? Any guesses?
It is to train the model, right?
True, obviously it's to train the model, but what does it happen when you put model.train in the backend?
Data flows through the model and the model trains.
Okay, maybe I'll explain it clearly. So, what happens when you put model.train is you have certain every weight, every bias is a tensor, and now when you're creating a tensor, you tell that the particular tensor requires a gradient or not. When you're putting model.train, you don't really you need to calculate the gradient placeholders for each of these weight parameters, which will be used in the backpropagation. That is one advantage. Second advantage is when you're using techniques like batch normalization and dropout. If you remember these techniques, both of them are on, or you can say are used during training time, and simultaneously both of them are switched off or not used in the test time. So with this model.train, functionalities like those will be taken care of. So dropout will be set to true if it's model.train, whereas even batch normalization will be calculated. If you don't set this, it will. I think another option is model.eval. It is model.train or model.eval. If you see here, if you set model.eval, it means that dropout is not used and batch normalization is not used. So these are again any functionalities which are dependent on train and test. Those all will be taken care with model.train.
So are you saying like previously what we did using the transfer function, like for the normalization, we won't be needing it to do it here as a model.train would take care of it.
Oh no, that is a different normalization. I'm talking about batch normalization. That is different normalization. That is where you're normalizing your input images to 0 to 1. Batch normalization is when you're training, right? In that particular batch of images, you normalize again the data set. That is different.
Uh,
Please be careful about that. Normalization is different from batch normalization.
So can you please elaborate batch normalization further?
Okay. So batch normalization, as discussed in the last class. So basically, in what happens is in your particular batch, like for example, in our case, you have 100 samples in a batch. So this 100 samples will go layer by layer, right? When in one forward pass. So after the first layer, there is a high chance that all the 100 images ranges will become different. So each of the input node might get a different range out of it. So now you want to normalize this entire what do you say hidden layers inputs to a certain similar range, just like how you do in normal normalization. So how to do that? You use this technique called as batch normalization, where you calculate the running mean and standard deviation of the particular batch which you're giving across different batches. So I've explained it in a very fast way because I that is not covered in this week. But if you're not clear, we can talk about it after this session. I'll explain it clearly.
Okay, thank you.
Okay. So first we set the model to train. Again, a bunch of different variables which will be used to calculate accuracies and losses. Next important is the inner loop. Now this inner loop goes across the different batches in your data loader. So always remember, like for example, in our case, how many batches do we have? 200. So this particular inner loop runs for 200 times. After that, only you say one epoch is done, but the model updates after every mini batch. So in this inner for loop, the model updates 200 times. So sometimes people gets confused that epochs, after each epoch the model gets updated. That's not true. We don't talk about it in theory a lot because in theory usually people say after every iteration we update, or every mini batch. People don't explicitly say after every mini batch you update. So but actually what happens is your epoch is considered to be done only when you run only when you pass through all the batches in the data set, and after each batch you do an update. And so in total in an epoch there can be multiple updates that can happen to your model. Just have this distinctions very clear between what is a epoch, what is a mini batch, and when does the model actually update. Okay, so this mini inner for loop is where we pass through the all the batches in the train loader. So it's simple, you write for inputs comma labels in train loader. You just call those two values. Here, this is again an important step. move your data to the device, same GPU device or same device as it is on your model. If you don't do this, you'll get an error saying that your model is on a different device, whereas your data is on different device and computations can't happen. Okay. Once you do this,
Like this, I didn't understood this, like the device thing. Like how is it different?
so okay, your let's just take notebook itself, Colab notebook. You'll have two devices, right? CPU and GPU. By default, all your images, model, everything what you create, right? It is created on the CPU device. So now, if you want to do the computations, you can do on CPU also, but it will take a lot of time because you're not using the power of GPU. So to use the power of GPU, you have to tell your computer or the system to send my models which I created and the data which I created on CPU to a GPU. Then once it moves to the GPU, then whatever code you've written, right, which is GPU optimized, will actually use the models, will actually use this functionality to make your training and everything faster of the models which is present on the GPU. Is that clear?
Yeah, yeah.
Yeah. Okay. Once you send your data to the GPU device, all your update is just these I think it's 5 steps. That's it. Your entire neural network update is just this 5 steps. This includes your forward pass, backward pass. In the forward pass, you just calculate the from each layer input output to the final output. You calculate your loss in this third line, and then you calculate what is the gradient of that loss with respect to the output, and then you back propagate that entire back propagation. That is also done with this loss dot backwards, and then you update each of these weights also using the grade whichever particular optimizer you have, right? Using that particular optimizer you update. All these different things are done in just these 5 lines. So let's go step by step. So let's first, I'll come back to the first statement, zero grad. Let's go to the second line first. Second line says outputs is equal to model of inputs. So what is this statement? Basically, this model is what we created on the top. Obviously, what are you sending inside that? The inputs which you get from the above statement. That input you're sending as an input to the model, and then you see, right, the in the forward function what we wrote above. So this x over here is your inputs, and this entire calculations happen, and what we are returning, return x. This is the output that is being returned, which will be stored in this outputs. So once you get your outputs, you obviously have your labels, and you can define whatever loss you want. For now we call it criteria, but you can define what loss. I'll show you out in the next section. This loss is usually a standard cross entropy loss. So this loss is calculated with the help of outputs and the ground truth labels. And now loss dot backwards is where you tell your model we are starting the back propagation. So you create all the gradients values, right, which you previously knew this gradients, whatever you want to calculate. You basically start tell your model basically, okay, now we are backward uh, passing the data. So that's what this loss dot backward does. And then optimizer dot step is where you actually update all your weights, each weight and bias, right, using that update rule of previous weight minus learning rate into gradients. Those things updates basically in this optimizer dot step. So these are it. So then what is this use of optimizer dot zero grad? Any guesses? Maybe you guys, because now I told you what is happening in this 4. After this will happen for first iteration. Now in the second iteration, optimizer dot zero grad starts. Why do we have to start with optimizer dot zero grad? It basically, I'll tell you what is in usefulness of, I'll tell you what is meaning of this. It basically sets all the gradients of all the weights or biases to 0. But why do we have to set this? Any guesses?
Maybe to clear off previous step gradient.
Yes, that's correct guess by Tapas. So you basically, sometimes what happens is your optimize the gradients, previous gradients might be just lurring around in the next iteration also, and that actually can mess up your update rule, update values. So it's always important with optimize to start off with optimizer dot zero grad, or either you can write it on the top or you can write it after optimizer dot step, but have it after you do one update in one iteration. Mention it somewhere either on the top or on the bottom. A good exercise would be remove it and see how much does the accuracy vary. Is that really important or not? You'll only see interesting results. Okay. So once these 5 steps are completed, you are updated the model, and now next is basically simple calculation of how much is the accuracy and what is the loss. Loss value anyways got it from the criteria. You don't have to worry about it. You just keep on calculating the losses. And if you want to calculate accuracy, you just do torch max. So out of the all the outputs you got, you identify which is the maximum output predicted class, and then you check is predicted class equal to the ground truth label. If yes, then you just sum it into the correct label, correct variable basically. So this is a standard way to do your accuracy calculation. There's nothing particular to PyTorch or anything. And then you store all these accuracy history, train accuracy, loss accuracy, and after you update, right? Sorry, after you finish passing through all the batches in one epoch, then you do eval. So this eval is for that one particular epoch. So in an epoch, you get two values output, right? What is your training loss, training accuracy? What is the validation loss, validation accuracy? So training loss and accuracy is done after you loop through all the batches. After that, you go to the eval where you loop through again all the validation set, and same process again. You loop through all the input and labels in the test loader. You send it to the model. You get the outputs. You calculate the loss. Here you don't have to do any update of the model because it's validation step. You just calculate the accuracy, and then you save those validation accuracy and loss, and that's what you're returning. 4 values: train accuracy, train loss, validation accuracy, validation loss. So let's just see how they created, how we can actually call these functions now. First, your leanet, you're creating an instance of that, an object of your class leanet, which is basically this small leanet. Similarly, you create an object of AlexNet and VGGNet. Then you're defining what loss function you want to use, which is this cross entropy loss. So previously, if you remember, I said don't worry about softmax, just
So what is this VGG CFG we're sending to the VGG network?
yes, so VGG CFG is basically a config file that actually defines what the network should look like. So every model you define a config file, bigger models, not the smaller models. Every big models you have a config file which defines how many layers you have, how many convolution layers, and each convolution what is the stride and all. Because sometimes the model is very huge, right? You can't write in this what do you say, step by step manner in sequential and all. So for that you create a config file, and that config file is what we use this here. Make layers. We'll take that config file and create this all layers. If it's a convolution, it creates a particular type of layer. If it's a max flow, it creates a particular type of layer. This is used whenever the network is very huge. So don't worry about it if you're not understanding it right now. This happens when you're creating bigger networks. But just imagine it to be not similar to what we're creating here. But when you have a huge model, it's easy to write a config file and just call this config file in this make layers, which will create layers automatically instead of you writing each layer separately. Is that clear?
Yes, sir, got it.
Yeah. So that's why you didn't see convolutions in the VGG, because there are a lot of convolution layers and we just write it as a separate config file. Okay, coming back to the loss. So I said, right, don't worry about returning X, don't worry about softmax when you're returning from the for function, because cross entropy loss inherently does the softmax. It takes input as logic, converts them into softmax, and then calculates the cross entropy loss. So that is inherently there in this nn dot cross entropy. So you don't have to explicitly write your softmax function. And then here we try different optimizers for different networks. Adam we try for LeanNet. Adam again. Oh, sorry. Here it's a different optimizers. Basically 3 different instances of the same optimizer because we have 3 different networks, right? So make sure you have to obviously have to create 3 different optimizers, because otherwise, if you have the same optimizer for 3 networks, the values won't work because each of them will be moving across the gradient in a different way, and then there'll be a confusion. So it's basically good to have 3 different optimizers, even though the same one for 3 different networks. Here we use Adam optimizer. We need to mention what are the parameters. So that is nothing but just mention dot parameters. It'll take, once you mention, then it will know, okay, these are all the parameters using on which the update should happen, weights and biases. And you also define your learning rate. Learning rate is again a hyperparameter which you'll have to figure out. Standard practices are 0.004, 0004, 001, 0001. People also use 0.3, triple, 4 zeros and 1. Bunch of different values you'll have to try around for learning. Number of epochs is 20. After this, nothing. You're just calling this train underscore model function with all these values which you just created. Leanet, optimizer, you what is the criteria, and what is the number of epochs. Uh, sorry. Yeah, what is the number of epochs? And you're storing all of the values over here. Train accuracy, train loss, validation accuracy, validation loss. You just see a bunch of different outputs, like for epoch 1 is done, epoch 2 is done, epoch 3 is done. Similarly, then AlexNet is run. First you print the network, then complete all the epochs. Similarly, VGG. So if you see, VGG is a very big network. What is it? Starts off from 0 convolution to still good. So 30. So it has almost 30 layers of mix of convolution and max pool. So it's very big compared to AlexNet and Leanet. So that's why it's better to write a config file, because most of them are same values, conv2d, right? You can't just keep on writing conv2d, conv2d, conv2d. So you just write a config file, and that will take care of writing this conv2d. Again, this 30 layers is not huge in today's world. Today we have very, very huge models like LLMs and all. So it's even harder when you want to create models for LLMs when you're writing the network definition. Again, this also runs for 20 epochs. And now you just plot all the values. This is a simple matplotlib plots where you have, because all of these are lists, right? We stored everything in lists. So you just plot all these lists. So this is what you observe. Now let's go plot by plot. First plot is training accuracy. And you see there are for 3 different networks. Leanet is in blue, AlexNet is in orange, VGG is in green. So as you know, AlexNet, so here you can see AlexNet is working better, and it is almost able to converge to 100% training accuracy, which is a good sign after 20 epochs. Whereas you don't see a typical convergence for VGG. It means understandably also because it has more number of layers as AlexNet, right? So it takes more time for it to converge. So it is still increasing. So maybe after a few more epochs, it will converge properly. Whereas Leanet pretty much looks like it will converge. I don't think it will increase. So these are all just different inferences that you draw, or that you when you look at the plot, you make these informed decisions. Similarly, training losses will decrease because loss and accuracy are inversely proportional. Now, another thing is validation. So always make sure your model is not overfitting. How do you do that? When there's a huge gap between these accuracies and validation accuracies, right? It usually means the model is overfitting or something like that. So again, here also we see a kind of convergence for the Leanet, but AlexNet is still improving. Most likely it would have gone better after a few more epochs. VGG network, not AlexNet. AlexNet pretty much kind of converges. And yeah, these are all different things that you can look into the broads. Obviously, when you do more and more validations, right, like hyperparameter selection and all, you see a bunch of varied type of plots, which will help you decide which hyperparameter value to choose and all those things. Okay. Yeah. Any questions or anything? So this is all the code walkthroughs that was planned for this session. If there are any questions, yes, please go ahead, Mishka.
Why do we plot accuracy and loss together? Why not? I mean, if we plot only one, that will be sufficient, right? So what is the difference between
Okay.
accuracy and loss? Plotting these two, I want to know that.
Yeah, so you don't have to plot these two, like you said. It is inherently pretty much the same, indirectly proportional. But sometimes people just like to look at both the plots also. There is subtle difference in the inference because sometimes the loss is not drastically decreasing. Accuracy is it's more easily divided. Like if you see the scales, right, it is going from 0 to 100. How much did this decrease? 0.02 to 0.001. Not a huge, right? It's like it's just 0.1 difference. Not even 0.1. It's 0.001 difference.
Yes.
So you don't know if your model is truly actually reducing. If this is the best it can ever reduce or not. You can't see the steepness sometimes. All these reasons, because losses are usually smaller values, because all the weights and inputs are between 0 and 1, right? So loss will also be something small values. So because of that, accuracy is also used to see more kind of steep curves, like to know actually whether the model is training or not. So that's why you plot different things. Is that clear?
Yes, sir. It's somewhat clear.
Yeah.
Okay.
Sir, hello.
Yeah. Please go ahead.
Like this is out of this what I'm asking. So, like, may I know your research area? Like,
Okay.
what you are working?
Yeah, I'll just answer your question. Is there anything relevant to this? Otherwise, I'll stop the recording. We can discuss that after I stop the recording. Any questions related to the coding or the questions that we discussed? Any doubts or anything that has to be explained? If not, then I'll just stop the recording